Welcome back to part 2 of creating an orbiting system in Unity. Okay, we're at the point where if we press play, we're going to get a whole bunch of spheres surrounding our sun. We now want to put some forces on these spheres. So we're going to go back into our code and we're going to do this inside the update. Okay, so what you want to add in here is this. So let's go through it and you should see all the different pieces that make up that formula we had a look at in the previous lecture, which was Newton's law of universal gravitation. First of all, for that, we need to work out what the distance between our two objects are. So that's between our sun and any particular sphere. So we're looping around all of our spheres, as you can see here. So the code's going to apply to each one of them and the sun. The difference in this case is our radius between the two centers of the sphere. So that's going to be the position of the sun minus the sphere's position. So that's going to give us a vector from one to the other. Now the actual distance or the radius, which is float dist here, is getting hold of the magnitude of that vector or the length of that vector, which will give you the exact radius. Next, we're going to create a gravitational direction vector, and that's going to be equal to our difference that we worked out before, dot normalize, so that we can get a direction that we're traveling in. In this case, the force is going to be pulling the planet towards the sun. Remember, the sun itself doesn't have a rigid body on it, so it's not really going to move around. Next, we calculate what the gravity is. Now, this, what I've called gravity here, is the F, or the force in that equation, and it's going to be 6.7, which is sort of a rough value for G, multiplied by the masses of the two objects that are involved. Now, in order to work out what the masses in this case are, because we didn't actually set a mass in the rigid body, which you can do in Unity, but we haven't done that. I'm just saying that the mass is going to be directly related to whatever random scale the planet ended up getting. So in that case, we're going to use the local scale of the sun, which is this. Now, X, Y, and Z are all exactly the same, so it doesn't matter which one you pluck out, multiplied by the sphere's local scale as well. Now, both of these values can be multiplied up in order to increase that gravity. Because if we try and simulate this in Unity using the actual value of gravity, which you saw with that G value is really, really, really tiny, pretty much nothing's going to happen in your system. So we're going to ramp that up a bit. And in fact, you know what? You don't even need this 6.7 out the front here, which is the G value. I've just got it in there to show you this is where it would go in the equation. But because you're multiplying over here by some value just to ramp the whole thing up, you could just get rid of this and make it sort of fold into whatever you have here. Now, for the system that I've created, when I've got this 80 and above, the planets get quite sticky towards the sun. If you get this much smaller, you'll see that the planets just go past the sun and couldn't care less about it. So this is the value that you really want to play with if you want to balance your system. Then that whole thing, or at least this second part here, is then divided by your radius squared, which is distance times distance, which is that value there. So we've calculated our gravitational force towards the sun. We can work out what the gravity vector is that we need to add or push our planet with by multiplying the gravity direction by that force. So this gives us our vector and magnitude of the force. So the direction we should be applying to the force to the planet. We then use the rigid bodies add force method to add that force to the planet. So you can see that I've added it just in here. Now, this add force method is using the setting of force mode acceleration. The reason being is that most of all of this simulation we're doing with our own mathematics. We're not using Unity's physics systems natural mathematics. So when you normally add a force without this bit in here, the acceleration, to an object in the unity physics system, it will apply that force based on the mass that you've set for the rigid body. Okay, so if you can remember another very famous physics equation, F equals ma, is that a force being applied equals the mass of that object multiplied by its acceleration. And in unity, the rigid body can have all those different settings, and therefore you can add a force and simulate what that force will do to a certain mass. So something that's much larger in mass is going to be harder to push with a certain force. But in this case, because we're doing the maths ourselves, the use of this force mode dot acceleration means it will add the force we give it without any bias whatsoever towards the mass of the rigid body. And that's because we've already built the mass of our rigid body into our equation by multiplying in our scales. Okay? So we're doing the work, not the unity physics system, although it's kind of involved when there's collisions and that sort of thing. But if you wanted to try and simulate this without force mode acceleration and by putting different actual masses on your rigid bodies, then go ahead and you can just add a simple force to them. Then you won't need to do these fancy calculations. But these are showing you what Newton's formula is exactly in code. Right, so we've got that. Let's save it and we'll go back to Unity and try it out. Right, so press play and we should get all our planets created and they'll start to get a force added onto them. Make this a bit bigger and you can see they're now coming in towards the sun. Now, any particular rotational movement that you might see there in the trails is from the collisions that's happening to the spheres. And eventually you end up with this sun that's kind of like a magnet and it's sort of collected all of these spheres together. So even in itself, this is actually quite an interesting result, even though that's not what we're going for. And they're just going to keep piling on and piling on. This is the result of the gravitational force when there is no other force associated with the planets. But in real space, and the reason that planets don't fall into their sun is that they're also moving at a sideways force as well. And that's because they were initially moving at a sideways force all on their own until they encountered the gravitational mass, which then started to play around with their movement. So let's now add in that initial force and see what happens. Right, so back to the code, and we're going to add in our sideways force. Now, this force that you add in doesn't really matter what it is, as long as your planet has some particular force that it started moving with when it started life. And we'll put that just above where we add in our gravity vector. So it's just one line that you need to add where you're adding a different force to your sphere. In this case, I'm just going to push the sphere forward along its z-axis, again with the same force mode dot acceleration. And that's all I'm going to do. And that's all I need. I just need some initial force that it was going along with before it encountered the gravitational force. Now, remember, the gravitational force is related to the distances between, or the distance between the sphere and the sun. So as the planet itself is actually moving, the amount of gravity on it is going to change, which is what makes this so interesting. Okay, so let's save this and let's go back and play, because it's quite remarkable the effect that you get doing this. And you will start to realize how many planets and other astronomical bodies had to be present in our solar system for us to end up with just the planets that we did, and the actual chances of it happening. So at the beginning, things are very chaotic, and you can see the forward direction of all the planets as they're moving away from the sun back into the distance in this scene. Most of them are far enough away that the gravity of that sun is not affecting them. And you can see off they go, and they'll go forever and ever and they'll be gone. But others have been captured by that gravitational pull and had their movement changed. And you can see now that we're getting a solar system start to appear out of it. There you can see the big band of the spheres that weren't affected and are moving off into the background, but you've got others, and even all the way out here you've got orbiters that are way out here orbiting at a great distance, because the balance is just right between their forward force, the direction, and also the force of the gravitational pull towards that sun. And it's just fascinating. I love this sort of stuff. Okay, so that's it pretty much. You've created a simulation of how orbiting occurs. You've not actually programmed orbiting, but something that evolves into an orbiting system. So I hope you enjoyed that, and I'm sure that eventually I'll get around to turning this example into something that uses the Unity job system. Thanks for watching. Please support the development of more superb online learning content by subscribing, and as always, visit holistic3d.com to learn more about awesome games development books and tutorials.